Welcome to the next chapter on multiple view geometry. Today we'll go a slightly different direction than what we've been going in the last couple of lectures. In the last lectures we talked about reconstruction from point correspondences. We said we assume we are given a set of correspondences. We actually talked about how to estimate these correspondences, and once we have the correspondences we can use linear algebra techniques in particular to factorize the structure and motion problem. That is to say, to separate the problem of camera motion estimation from the problem of structure estimation. But the way we estimate structure is really, what we mean by structure in these methods is for a few selected points where we have correspondences, we compute their 3D location. The question is that really sufficient? And as you know, the world we live in is a continuous world in many ways. So I have geometry everywhere, objects everywhere. If I just reconstruct a few selected points, what am I going to do with that? I didn't actually mention how people traditionally have solved that problem, but you saw it in one of the early results. You typically fit a mesh through these point correspondences, through these 3D points. So you have a sparse set of 3D points and then you connect them with say a triangular mesh. The question is if that is a valid strategy, because honestly you don't know anything about the space between these points. So I tell you, this point is a 3D point that I've reconstructed, so that lives on some object. This point as well, this point as well. Well, you know, can we fit a triangle in between? Is it really linear in between? Is that a good approximation? We don't know. The hope and the assumption is that objects are sufficiently smooth, or you know, locally you can approximate them with a plane, and that if you have enough points, if you're close enough, if you have a sufficient dense reconstruction, enough points reconstructed, then you can locally interpolate. If that's a valid you know, assumption, if that really gives a good reconstruction, is a separate matter. But the reason why this was done is because the reconstruction problem is a very involved one. It's very, you know, it's a big problem to really reconstruct the entire world around us, and so working with sparse features allows us to at least get a fairly fast reconstruction. And in fact, these sparse feature point based techniques, or these techniques that recover the camera motion and the 3D location of a sparse set of points, these methods are nowadays at a level where you can run them in real time. So you can have, and I might demo that to you at some point, you can have algorithms that track the motion of a camera while you're moving it, and that tell you the location of 3D points in a way that you can even do things like object insertion into in say augmented reality, right? You have a camera and you say you film a table scene and you want to place a virtual object as if it was standing on that table. And you all know that. I mean, you know, Hollywood does that every day now. But the question is, are we at a level where we can do it in real time? So while I'm moving the camera, can I insert an object in the scene? Question is, do you want to have it in real time? Of course, in Hollywood they don't care. You know, you can run the computations overnight and over weeks maybe, and in the end the movie comes out. But there are applications where you need it in real time. One application that is getting more and more important is surgery, interactive surgery or computer-assisted surgery in medical domain. You have the doctor, he has a camera, and you want to say superimpose where is the liver so the doctor only sees the outside of the patient but wants to know where's the location of the lungs, of the liver, of whatever tumor he's supposed to extract. right? And in that scenario, you may want to superimpose that in real time, so that when, say, the doctor can have a head-mounted display or with some glasses, and while he moves around, his location is tracked, and then you want to superimpose a model or something. So these are applications where you need the structure in real time. And for sparse approaches, this works. You can get it in real time. And people have focused on the sparse approach because the dense approach, where you really reconstruct geometry in every spatial direction, let's say, is more involved. But fortunately, what we see today, over the last 2 or 3 years, we've seen more advanced technologies emerge, also faster processing technologies, say graphics cards, etc., which allow to do dense reconstruction in real time. So not only for a sparse set of feature points, but for the entire the entire image plane, you want to determine where is the geometry. And one strategy to do these, and this is what I wanted to talk about in the end of the class, so the idea here is to bring in some of the more state-of-the-art dense reconstruction techniques. So this is not going to be in the spirit of linear algebra anymore, and you will see there's a number of differences. The key difference is that the computational paradigms are very different. And the key computational paradigm that has emerged as extremely powerful for 3D reconstruction, but also for many other problems in computer vision, is the so-called variational method. Has anyone heard of that before? If you have not, and if you find this might be interesting to you, I'm giving a class next semester in fall on variational methods. So this is an entire class completely dedicated just to variational methods. So here what I do, I explicitly wrote a very short intro. So this is not going to cover the entire field of variational methods. We cannot do that in 2 or 3 hours, but I wanted to give you a little bit of a glimpse here. And so there's going to be 2 parts. Chapter 7 will be introducing the variational methods, the key ideas, and then Chapter 8 will be how to apply them to dense 3D reconstruction. In particular, I'll talk a little bit about variational methods, what they are in general, and then what's always useful in this context is to have one specific application, an example of a variational method. And the most, say, intuitive example is the so-called image smoothing or image denoising example, and how to do that in a variational setting. And then I will come to the key kind of component of variational methods, the so-called Euler Lagrange equation, and I will mention the gradient descent, and then I will also show that you can enhance variational methods very easily and do adaptive smoothing. Smoothing where you blur noise but preserve semantic information. And this has always been a challenge in image analysis, that you have images that are perturbed by noise. You want to remove the noise, but you don't want to remove the signal. And this challenge, how do I separate signal from noise? How can I remove the noise but preserve the signal, is an important one, and variational methods are almost ideally suited to tackle these problems. And then I will lastly mention a little bit about Euler and Lagrange, the 2 mathematicians who pioneered this field a long time ago, actually. Variational methods are a class of optimization methods. I'm sure many of you have heard of optimization methods. The variational methods are a specific subclass of optimization methods. They're very popular because they allow to solve many problems in a very transparent manner. So in practice, what that means is, instead of proposing some algorithm. Let's say someone gives you a problem to solve, and then you cook up some algorithm. I take the image, then I look at the pixel colors, and then I take neighboring pixels and take their difference of the intensities, and then I threshold that. You know, there's so many kind of heuristics that you can apply to an image, and that has been done for decades. In the 80s, in the 70s, the early image processing is like that. Engineers or other people, they took images and just checked what can I do with pixel colors, and if I apply a certain recipe, what comes out. And you can get very far with that, and that's been kind of a lot of groundbreaking results or work has been done in that field, and the first working image processing techniques. But in the end, the problem is you have like a cookbook recipe. And the advantage of variational methods and optimization methods is that you tackle the problem very differently. You don't tackle it by some procedure, but you tackle it in a way that you say, what is it that I want from the solution? So you first sit down and say, I want to solve this problem. What does that mean? What do I expect from my solution? What properties should this solution have? And then you specify mathematically the properties that you want from the solution, and then the algorithm actually falls out naturally in some sense. You just say this is the optimization criterion, and the solution is the one of minimal cost, let's say. We'll see examples in a second so you get a better understanding. Variational methods are particularly popular for infinite dimensional problems and for spatially continuous problems. What do I mean by infinite dimensional? If we talk about 3D reconstruction, that is a problem essentially of infinite dimensions. How can you see that? Well, let's say I'm giving you a number of images of some statue. There's the statue, you take images, and I want you to reconstruct the statue, the 3D geometry of the statue. One naive guess is to say, oh, maybe the object is a sphere, right? Which is typically a bad guess, but let's say someone says, well, could be a sphere. That's one possible solution to the problem. May not be the right one, generally it's not, but it is one possible geometry. It's a surface in 3D. Now let's say you want to try different surfaces. Starting from that sphere, you want to check, what is the right reconstruction. So you perturb the sphere. You can do that at infinitely many points. You can take the sphere and perturb it in infinitely many ways and get a different geometry out, right? Why infinitely many? Because there are infinitely many points on the sphere, and for each point I can perturb the sphere in the normal direction and I get a new geometry. And so the space of possible surfaces is infinite dimensional, because starting from the sphere I can move it, I can change it, perturb it in infinitely many directions, and each of these directions is a separate dimension to the optimization problem. So often I find in our society people are scared by the term dimension. They say, oh, we live in a 5-dimensional space, and when you read newspapers, they always talk about lots of dimensions. You shouldn't be scared by dimensions. Dimensions are just a mathematical way to represent solutions. And if something has 4 or 5 or even infinite dimensions, shouldn't be scary, really. The variational methods can be used for, as I said, many problems. They were pioneered for image denoising, for example, image restoration, where you assume you have a signal perturbed by noise and you want to remove the noise. Image segmentation is one of the most popular topics in image analysis, is when you want to group the entire image plane into meaningful regions, right? So if I give you an image, maybe here's an image and there's a person or something standing in the image, then you want to separate what is the region associated with the person and what is the region associated with the background. Sometimes this is called figure-ground separation. You want to separate the figure from the background. And sometimes it's called segmentation, because you partition or decompose the image into a lot of segments. In this case, maybe 2 segments, one for the foreground and one for the background, but possibly you're going to have multiple people, or you want to decompose the person into head, torso, arms, and then you have a multiple region segmentation. Motion estimation, optical flow. If you have multiple images, consecutive images from a video camera, you want to estimate where do things move. We already talked about this in this class. You can tackle that with variational methods. In fact, one of the works that we mention in the context of correspondence finding, the work of Horn and Schank. Horn and Schank, 1981. That is often considered the first variational method in computer vision. So this is quite pioneering in that sense. And object tracking, multi-view reconstruction, if you do it in a dense way, we'll see what that means later on, then you can tackle all of these problems with variational methods. And in addition, often these variational methods are among the most powerful techniques. Typically, once you have an optimization or a problem, there are many ways to solve it. But it turns out over the last years, for example, if you look at optical flow, the state of the art, the most accurate flow estimation techniques are variational methods. And so among hundreds and thousands of algorithms, the variational methods have been dominating that field for the last years. Why are variational methods good? They have many advantages, in particular when you compare variational methods over these heuristic multi-step approaches. You may not be so familiar with, does anyone know the canny edge detector? It's like a standard edge detector. If you go into what the detector actually does, so if you don't just call up the MATLAB algorithm and apply it, but if you actually go into the paper and check what did Canny suggest to do, it's very complicated. So there's, a lot of separate steps in there, finding regions of strong gradient, then, thinning out the regions, connecting them to curves, doing non-maximum suppression, and, a whole bunch of techniques that he applies one after the other. This is how image analysis was done in the 70s and 80s. And I should say, unfortunately, still today, many people work in this way. It's very intransparent. Why is that? You don't have a clear idea of what this is getting to, this sequence of processing steps. You cannot, for example, in a variational method, instead you can study this optimization criteria. And so the idea, to put it very simply, is you define your solution space. So this is the space of possible solutions. For example, the space of all 3D surfaces. And on that space, you define a cost function that's often called an energy for historic reasons. So for any solution S, I have an energy E of S. Any surface in 3D, I have a cost that tells me how good is that surface. How well does it match the observations, for example. And so you have this cost, and then you say, I want to find the solution S optimal, the one that has the lowest cost. That's the idea. This is the idea of optimization methods. And the nice thing is, once you have defined your cost function, you can actually study it. You can analyze it. You can say, does it admit the solution? Is there a solution of a certain, say, smoothness or regularity? You can also study uniqueness. Is the solution unique, yes or no, or are there possibly multiple equivalent solutions? It could well be that we have an energy which has another minimum of the same size, so there's actually multiple solutions of the same cost. All of this you can study by looking at the cost function. So without actually having an algorithm to compute it, you can just by analyzing the cost function, you can often determine, is the solution to this problem unique or not. In addition, we don't have this multi-step approach like I mentioned. The Canny edge detector is one such example, maybe one of the more prominent examples, because it's been very popular in image analysis. The issue with these multi-step approaches is the way you would visualize them is you have an image here, and then you do something with the image. You do processing, and you do something else with the image, and something else, right? And in the end, you get some output. The issue is, if you have this pipeline of processing, and then you say, oh, this here is not so good, I'm going to replace this component with a better component, then you have to re-engineer the whole rest of the pipeline. Because the output is going to be different, and this component uses the output of that. So if the output is no longer the same, it's very much like in a factory. If one worker builds up on what the previous worker has done, and then you replace that person in the pipeline by someone else, this is not going to work well, at least for the first couple of weeks, until that person figures out what his job is, etc. Right? And until the others adapt to the output of this one. So it's a very complex engineering that you have to do to actually get it to work. As a consequence, people use the Canny edge detector, but they're likely not to change things, because if you tweak one component in the middle, then the whole output no longer looks the same. So it's very hard to predict what is the effect of modifying some component. And so that's very bad for research, because you want to modify things, you want to improve things. You want to start with a working solution, but then you want to be able to tweak it, to modify it, to get better solutions. In this multi-step approaches is a very nasty business to try to change things. Instead, in the variational methods, all assumptions are very transparent. It's very clear what you're aiming at. There are no so-called hidden assumptions. Often, in the multi-step approaches, if you look, what does this module do? Then, by looking at what it does, you figure out indirectly what are the assumptions somehow. For example, in the Canny edge detection, if it finds regions of strong intensity gradient, there seems to be the assumption that an edge is a location where the brightness changes. But it's not really explicit. It's somehow in the cookbook you figure out, oh, this is why they put that. But you want to have these assumptions really out on the table, so to speak. In addition, variational methods typically have fewer tuning parameters. This is very useful in solving real-world problems. You not only want a method that solves a problem, but often you want a method where you don't have to tweak too many parameters to get the right solution. And in this multi-step approaches, each of these components has 2 or 3 tuning parameters that you can tweak to modify it. For example, the thresholding in the Canny, or the edge detection, or there's lots of little parameters in each of these components, and it's very hard to figure out how do these components interact. It may well be that if you change some parameter in the module 1, if you increase that parameter, then you need to decrease some parameter in module 3 to compensate, right? That is quite possible. So there is a very unpredictable, relation between the parameter values here. The other thing is, with variational methods, they're very easily fused. The way you fuse in a variational setting is if you have an energy E1 that encodes some of the things that you want from the reconstruction, and then you have another energy E2 that encodes other properties which you also want, then you just define an energy E as E1 plus E2. Maybe with a weighting alpha, let's say, or lambda it's often called, and lambda is some non-negative parameter, and then you say, now I want to minimize that E. What it gives you is a solution that has both a low energy E1 and a low energy E2, meaning it somehow aims to find a good compromise of the two. And so from an algorithmic and mathematical point of view, this is quite easy to do. You know, just add the energies. Whereas if you have one processing pipeline and someone has another processing pipeline to get some output, and now you say, I want to combine somehow the knowledge of the two, or it's not clear how you do that. So I should say these advantages of variational methods. I wrote advantages of variational methods, but they mostly also hold for other kinds of optimization methods. So this is not just restricted to variational methods, but to optimization methods in general. The variational methods are typically defined in a spatially continuous setting. Maybe to say one word about why they are called variational methods. There is the notion of varying something. What you do in variational methods in order to determine solutions of low cost is you start somewhere, S0, and then you vary or perturb the solution in a way that the energy goes down. And then you may find this S optimal one, let's say, a solution that is at least locally optimal. And this is the idea of variational methods, that by varying the solution, I find a better solution. So here's the idea. I've made it more specific for gray value image denoising. Maybe I'll draw another picture to give you the idea. Let's say you have an input signal that looks like that. And so there is some signal, and the assumption is that the noise is on a high frequency scale, on a small spatial scale, and you want to find a denoised version that is similar to the original but smooth. We will call the input image, I will call F, and the output, the denoised version, I will call U, the green function here. And so if this is omega, then a gray value image, and that could be the image plane if you want. Typically it's two-dimensional, but it doesn't matter for now. You can assume this is the image plane, and this is the intensity of your input image, F. And now we say, so mathematically F is a mapping from omega to R. And we assume that this observation arises from some true image, but it's corrupted by noise. This is a very common assumption in signal processing, that the observed signal is, that the observation is the true signal plus some noise. So this is a model of additive noise. You can have other kinds of also multiplicative noise, but here we assume additive noise. And what we are interested in is finding a denoised version U of the input F. And so this is the problem. And now how can we put that problem into an optimization setting? I said there are two things that this solution should fulfill. So this is what we state up front. What do we want from the solution? The first thing is, of course, it should be similar to F. You know, F is the observed signal, and the reconstruction should be in some sense similar. Similar is a bit vague in terms of mathematics, but it conveys the idea. And how you measure similarity is then a separate question, but we say it should be similar. Secondly, we say the noise-free reconstruction should be spatially smooth. That is an assumption that we put in. The assumption being that the noise-free, so the true signal, is such that from one point to the next it should be similar. It should not oscillate like the noisy version. And we can enter both of these criteria into a cost function. That's the idea. And the cost function has two components. One that measures that similarity is called a data term. It measures how well does the reconstruction match the data. And the other is the smoothness term, or sometimes called regularity term. It measures how smooth is the reconstruction. And by adding the two energies, we say we want a solution which firstly is close to the input, the measured intensities, F, and secondly, it is smooth. And so very much like what I said, you have two kind of constraints or two criteria that you want to fulfill or optimize, and you just add the two, saying I want both of these criteria fulfilled. Of course, what is neglected here is when you add them, you typically have a weighting where you say how much do I impose smoothness and how much do I impose data fidelity. And that's often up to you to decide, do I trust the data more or do I want smoothness? It depends on how much noise you have on the data, for example. It's interesting that for image smoothing, the variational method looks like that, a data term, a smoothness term. It turns out that for pretty much all variational methods, cost functions have this form. They typically consist of two energies. One is a data fidelity term and one is a smoothness or regularity term. Here's what that could look like in practice. You know, how you measure data fidelity, how you measure smoothness is really up to you or up to the specific application you want to solve. But these are two examples that I give of possible energies. The data term, for example, what we can do is for every pixel in the image plane, so here we have an integral over all pixels. Don't be scared of integrals. If you attend the class in fall on variational methods, you'll see lots of integrals. Really, it's nothing but the sum, right? I mean, this is important to keep in mind. You're just summing over all the pixels of the image here. And for every pixel x in the image, I say the reconstruction should be similar to the signal. And similar, I mean in terms of the L2 norm. This is called the L2 norm. It's just the quadratic difference, the sum of squared differences, if you want. This is the most common energies are typically quadratic energies. Why that is a separate topic, but one reason is they're very simple and lead to fairly simple algorithms. The smoothness term, we said we want the reconstructed signal, the denoised signal, should be spatially smooth, right? The green curve that I drew here, what characterizes that green curve is it is smooth. And smoothness means nothing but that from one pixel to the next, the function u should not change too much. Ideally, it should stay constant, or at least the changes should be small. And now changes in math are computed using the so-called gradient. That means the derivative. How does the function u change in x direction and in y direction if I have a 2D image? By the way, in terms of notation, when I integrate, you see here dx, this actually is a d2x. Often I drop that. So strictly speaking, if you separate it in x and y, you would have u of x and y, f of x and y, and then you would have dx and dy. But now you see why I don't write that out, because it just complicates the notation. So when you see x here, this is a two-dimensional point, and dx is actually has two components. And similarly, the derivative has two components, an x derivative and a y derivative. This is called the gradient, for those who haven't seen that symbol before, the triangle with the point down. And what I'm penalizing here is the squared norm of the gradient. So at each pixel x, I want that the change in x and y direction should be small. Right? What's important, if you haven't seen a lot of optimization in the past, what's important, you have to look at these energies always in terms of the solution is the minimizer of these cost functions. And here it means I'm favoring solutions U where the gradient is small. Here again we square it. I will show you towards the end what you can do if you, for example, drop that square and just say I penalize the gradient, but I don't penalize it quadratically. And interestingly, you get a completely different result. I'll show you towards the end. So then I said minimizing the total energy, that would be a weighted sum of the data term and the smoothness term, so the total energy looks like that. Right, the data fidelity, L2 norm between the reconstruction and the observed signal, and the smoothness term is just the gradient squared. And then I have a weighting lambda if I increase the parameter lambda, and so that is my parameter. I have one parameter in that variational model. And that parameter governs very obviously the relative weight of smoothness cost versus data fidelity cost. And often people say, oh, so how do you determine lambda? What is a good value for lambda? You cannot say that in general. It really depends on your application. And it depends on how much do you trust the observation. If you have a camera that has very little noise, then the observed intensity is the true intensity, more or less. And so that term is important. Whereas if your camera is very noisy, you should not trust the observations too much because they're heavily corrupted by noise, and so you should put more weight on the smoothness term. And so that is actually something very general. The smoothness term typically reflects so-called prior knowledge. It reflects what you know about the solution before actually looking at the data. So the assumption here is that the world is smooth, that the intensities I see from one pixel to the next don't vary too much. That assumption for our world is actually not bad. If you look at the white wall, you know, from one pixel to the next, it's always the same white color. You don't see random colors, but the color doesn't typically change much. What is not very good is actually the quadratic norm, we'll see in a second, because it tends to over-smooth boundaries. What you have in the real world is you have regions that have homogeneous color, and then you have other regions that have a completely different color. And if you go from my shirt to the wall, you have a sudden jump from black to white. And so in the world, we typically have smoothness, but we also have discontinuities in the intensity. And so what we would want is something that preserves, that favors continuity of the gray value, but that allows for jumps. If you penalize the gradient quadratically, you tend to not allow for jumps. And so if you denoise, say, an image with a black and white structure, then the boundaries will be blurred by this term. And so the regularity term reflects what you know about the world, and in general the weighting is a question of how much do you trust the data versus how much do you trust your knowledge about the world. And interestingly, if you look into your own world, that is different for different people. Some people trust their eyes more than they trust what they know. And some people trust more what they know and not so much what they see. So this is the weighting here, so between the observation and the knowledge about the world. Here my knowledge would be the intensity is smooth, the true intensity, and the question is if that knowledge is accurate, if it really represents the world well, then I can increase that weight because I know this should be true. And so that's kind of the trade-off here, and it really depends on the application, how you set lambda. But what you can always do for a single parameter, you can try different values and see how the algorithm works. Such energies are called functionals in mathematics. So they are, E is a function that maps, that has as an argument a function itself and assigns to it some real number. Typically, these are non-negative numbers, and so this is called a functional. So in contrast to a standard function on R, I don't have a so in other words, the solution space that I have here, maybe to put it this way, that solution space has infinite dimensions. Each solution in itself is a function u of x, right? And so for each u of x, I have some cost associated with it. These are called functionals, and the key challenge is, how do I minimize such functionals? So now you have an idea how to set up a cost function that reflects some data fidelity, some regularity term, but now the question is, how do I compute minimizers? And the difficulty is that I'm really optimizing with not a finite number of parameters, but an infinite number. For each pixel in the image plane X, I can have a separate gray value. And variational methods are designed to minimize functionals, so energies that have as arguments functions. Here is one of the key results from variational calculus, and this is the so-called Euler Lagrange equation. And as I said, we'll have a separate class on variational methods in fall, so here I just summarize the key results. The idea of variational methods is to say that for a minimizer of this energy, a necessary condition is that the so-called Euler Lagrange equation must hold. Maybe to give you a drawing, the Euler Lagrange equation, I already drew it here, is nothing but saying that the energy at the minimum is such that the local derivative is zero. This is something you might remember from high school, right? When you have functions, you said if I want to determine minima or maxima or saddle points, then the derivative must be zero. So dE by ds at the minimum is zero. That is kind of the assumption here. That is a necessary condition. As you recall from high school, this is not a sufficient condition in general. If the derivative is zero, you may remember you could be at a minimum, but you might well be at a maximum. Or you might be at a saddle point, so a point which is neither minimum nor maximum. There, the slope of the curve is also horizontal, the derivative is also zero, but I'm neither at a minimum nor a maximum. But it's a necessary condition. And this is something that I'm just going to quote here and not prove because it's a little bit involved. You can show that for functionals that have this form, so u is defined on say omega, and now you integrate over all pixels in omega, some quantity that depends on u and on the derivative of u. This is, so u prime is nothing but the derivative. I didn't put it on the slide. So u prime is essentially what you had here, the gradient. So in one dimension, it's just the one-dimensional derivative. And here, so the L in the previous case would be u minus f squared plus lambda times nabla u squared. That is this function L is called the Lagrangian, it's often called. And then the question is, how do we do dE by du? How do we compute the derivative? How does, basically what this quantity tells you is, how does the energy change if I vary the function u? I start with some function u, maybe this one here, and now I vary it, and I can vary it at many points. I can say, oh, maybe I should increase the function here, maybe I should decrease the function here. So you can vary that initial curve at function at many points, and this tells you how does the energy change as a function of varying u. And you can show that for energies of this type, this variation can be written in this way: dl by du minus d dx times dl by du prime. And as I said, I'm not going to prove it. This equation is called the Euler Lagrange equation. And there's a whole variational calculus that allows you to derive this equation. And for anyone interested, feel free to attend my class next semester. There I will, among other things, derive this equation. So what we can say is, minimizers of the energy as a necessary condition have to fulfill this Euler Lagrange equation. I should say the truth is slightly more complicated. The truth is, this is only correct if the energy is differentiable, right? For example, if you have an energy that has a very sharp that is not differentiable here, then the minimum is here, but the derivative at that point is not zero. It's not defined at all. So this assumes, of course, that you can compute derivatives. But if the energy is differentiable, meaning you can compute the derivative everywhere, then at the minimum you should have this. The other thing is, this also only holds if the optimization problem is unconstrained. Let's say I have an energy that looks like that, so it just keeps going down, but then I have a boundary condition that says, let's say here is 0, that the solution should be larger than 0, so I minimize E of u under the condition that u should be positive, then the minimum is this point here. The derivative is not 0 either. So obviously this condition is a necessary condition in the case that your problem is differentiable and in the case that it is unconstrained. If you have a constrained optimization problem, the whole picture changes a little bit, but it's actually quite obvious when minimality has this equation as a necessary condition. And this necessary condition is called the Euler Lagrange equation, and so variational methods often boil down to solving the Euler Lagrange equation. And this is essentially what the algorithm then is. So the whole algorithm you get indirectly, so you start by saying, what is the problem I want to solve? You formalize it by putting it into a cost function, and then you say, now compute the minimum of this cost function, and in the variational setting you would say, compute a solution to the Euler Lagrange equation. There are many ways to compute such solutions. One is you can directly compute this, write down this equation and try to solve it directly. Sometimes that can be solved. For example, for this problem, you can directly write down the Euler Lagrange equation and solve it. Why is that? This function here is quadratic in u, right? You have u minus f squared, that's a quadratic cost function, and here is also quadratic. Meaning if I compute the derivative, then I get a linear equation system. This is one of the reasons why quadratic energies are popular, because in the variational formulation is a linear equation system, and solving linear equations is standard. There are many techniques even to solve large-scale equation systems. One is called the Gauss-Seidel method or Jacobi method. So there are many methods to solve such equations. So that would be one approach. Write down the equation directly, write it out, compute this derivative, and then write it down and just solve the equation system. Another solution is the so-called descent methods. They are related but different. The descent methods, they also work if you cannot directly solve this equation system. The way the descent methods work is that they start with some initial, here's my energy plot, so here's the solution space, here's my energy. I start with some initial solution that has some initial energy, and then I vary it locally. How do I vary it? Well, I go here and check what is the derivative at this point. It tells me how does the energy change at that point. The derivative encodes the change of energy if I change in the solution space. And then I say, very loosely speaking, I check where does it go downhill. And so these methods are sometimes also called downhill methods or descent methods, because you just go down. So it's very much like if you, let's say you're in a landscape and someone asks you go to the lowest possible point. How would you do that? You would look around you and say, where does it go down? And then you select the direction that has maybe the steepest descent, where it goes down fastest. If you're athletic, you can probably take the steepest descent. If you have constraints, you don't want to go too steep, you might not want to take the steepest descent. But as long as you keep going downhill, it's a good strategy, because you're getting better and better. You're getting lower and lower. And that's what the descent methods do. And in particular, the gradient descent method is in some sense the method where for each step that I take, I get the most descent. And so these are, at least among descent methods, quite fast, because they get you down fast. Here's the gradient descent. This is again a result that I'm going to go more into detail in the class on variational methods. At a first glance, it's I find sometimes a bit confusing to students. But the idea is, as I said, you go downhill. It's called gradient descent. Sometimes it's called steepest descent. So the key idea is you start with an initial configuration. I said some initial solution. When I say initial, we really consider a temporal process of going towards the minimum. And that temporal process has a parameter, the time parameter, and for time 0, so at the start, we have some initial configuration. Let's call it u0 of x. So that is our initial configuration at time 0. So what I just did, you see, is now I don't have just one function u of x, but I have a family of, say, approximations u of x parameterized with the time parameter t. And the idea is for t going to infinity, this process that I describe here goes to the minimum. So in other words, I have some initial solution with some initial cost, and step by step the cost is decreased. Step by step I go towards the optimum, right? And this iterative process of walking towards the minimum of the cost is called the gradient descent. And what you already see here in the drawing is it does not, for general energies, it does not give the provably optimal solution. It does not give me the configuration of lowest cost among all configurations, but at least in a certain vicinity it gives me the best solution. And that is actually one of the difficulties in optimization in general. Once you set up a cost function, if it's an arbitrary cost function, there is no way to compute the provable optimum. If you don't know anything about the structure of your energy, at least in high dimensions, you cannot compute optima. In low dimensions, you can typically try all solutions, at least on a discretized level. I discretize the space of solutions, I try all of them and see which one is the best. If you have typically these solution spaces, as I said, for the problems we consider are infinite dimensional, so the drawing is very misleading. It's not a one-dimensional space, but you have infinitely many dimensions. And then you cannot try all solutions. And then often the gradient descent is the only thing you can do. If you have an energy in infinite dimensions and you don't know anything about the energy, gradient descent will lead you to the nearest local minimum. which is typically the best that you can do. Here's what this looks like. The gradient I already mentioned in the previous slide. dE by du is the gradient. If we go back one slide, here it is. dE by du is that expression for this class of energies, dL by du minus d dx dL by du prime. And for this specific energy, here I wrote it again, L of u and u prime, the data fidelity term, u minus f squared, and then lambda times the derivative square. You see I added 1/2 here, by the way. This is just a convention. It's important here. I didn't have the 1/2. I just had this term plus this term. But this is important when you do energy minimization. If you scale things by 1/2, it doesn't have an effect, right? All I'm saying is minimize this energy. Whether I minimize that energy or half of that energy comes down to the same. The energy is different, but what I'm interested in is the solution, so the minimizer of that energy. And so if a function u minimizes some energy, it's the same function also minimizes half that energy. And so I can add 1/2. You'll see in a second why I do that. The reason is simply that if I compute the derivative here, dL by du, for example, if I take the derivative of this expression with respect to u, then the factor of 2 comes up front and it just cancels with the 1/2. And so then I have f minus u. This is minus dL by du, so that would be f minus u from this term. And then this term is d dx dL by du prime. Here we have u prime. The derivative of this expression with respect to u prime is the 2 comes up front, and then I have lambda times u prime. And then I do another derivative with respect to x, which gives me u prime prime is the second derivative of u with respect to x. So this is just to show you, you can directly apply this calculus to a specific cost function. And what you end up with is an equation. So this equation for the image smoothing is exactly this one. And this is called the partial differential equation. Why is it called partial differential? It's a differential equation. A differential equation, have you heard of differential equations? Yes. So a differential equation is an equation that couples the derivatives of some function in some equation. And here the function is u that we're interested in. And here we have derivatives of u, for example, with respect to time, and the second derivative in space. And it's called partial derivative, partial differential equation, because you have a function that has two arguments, x and time, and you have derivatives both in the spatial domain and in the temporal domain. This is why often when you look into sciences, variational methods are typically hand in hand with partial differential equations. When you look at what people do research, for example, in image analysis, you have people who do variational methods and partial differential equations. Why? Because once you solve a variational problem, you immediately get into a partial differential equation. And so then the gradient descent means you have to solve this equation. It looks a little bit abstract and a little bit difficult maybe, but the key to actually implement it, I didn't write that on the slides because I didn't want to go too much into detail, but maybe to give you a little bit the intuition of what you end up doing to implement these methods. We have here du by dt is something. What we do in practice is that tells us how does u change over time. And we can discretize that derivative by saying that approximately u of x at time t plus 1 minus u of x at time t. Right? So that is a discretization of the derivative. The derivative is nothing but the change from time t to time t plus 1 is whatever the right-hand side is. And then I can solve that and say u of x and time t plus 1 equals u of x at time t plus the right-hand side here. And so I have now a recipe that tells me how do I get the u at the next time step from the old time step. All I do is I take the old solution and I add whatever is the right hand side here. This is called an explicit Euler scheme. So this is the simplest way to discretize these differential equations. And so in the computer, then you would have a for loop over a lot of time steps, starting from t equals 0, some initial configuration, and with each time I just add the right-hand side, and then I iterate that over time. And that is what's called the gradient descent. And that gives me a family of images which get closer and closer to the minimizer of the cost function. I said in general this will only lead you to a local minimum. Here we are fortunate because this is an energy that is quadratic. This is quadratic, and this energy is convex. It looks like that. So it really only has one minimum. There are not multiple minima. And so this is another reason why people use quadratic energies, because among other things that they're convex. So that's essentially what this energy looks like. And so just by looking at this energy, I can tell you right away, first of all, there is a solution. And secondly, it's unique. There's only one solution. There are no multiple solutions because it's a quadratic energy. So just by looking at the cost function, you can already deduce there's only one solution to the problem. Of course, with different lambda, the cost function changes, so I have one solution for each value of lambda. So once you select the specific parameter lambda that defines how much smoothing you want, there's one solution only. And it's easy to compute. The gradient descent will get you to that solution. Here is what that looks like in practice. So if you take this energy, F minus u squared, nabla u, you see I have yet shortened the notation. This is of course f of x and u of x here. I dropped the dependency to simplify a little bit the notation. A quadratic data term, a quadratic smoothness term. If I minimize this by gradient descent, let's say I start with the initial image. This is the input image. This is f. Actually, I start with f. Why is it good to start with f? Well, I already know I want to be close to f. That term says I want to be close to f, so if I initialize with f, it means that term is perfectly fulfilled. I'm already the lowest possible energy with respect to this term. And then I have that smoothness term in addition, and so if I do gradient descent on this joint energy, meaning I solve this equation iteratively, then in the iterations I get more and more blurred images. So what you have here on the right is then a solution, and the solution means it is in some sense close to the input image, but it is smooth in the sense that from one pixel to the next the brightness doesn't change too much. And so you see that a lot of, and this is not very impressive actually, because it's something that we all know. It is exactly what a lens does, a lens blurring does to an image. If you observe an image through a lens, it blurs the structure, and this is what it looks like. So for example, if you take a picture with a camera and the camera is out of focus, that's exactly what it looks like. What we can also do is we can just minimize the smoothness term and initialize with the image. If we do that, we get almost the same behavior as you see, except that if I keep iterating this, what do you think is going to happen? So this is the gradient descent on just the smoothness term. What do you think will happen? Yes, exactly. It converges to a constant gray image if I keep iterating. Why? Because indeed, that is the minimizer of this energy is a constant. If you have a constant function u, the gradient is 0, and since this is a non-negative energy, 0 is the best you can do. So this is the difference between this energy and that energy. This one still has a data term there, so if you keep iterating, it will not become constant because you have the data fidelity term in there. Whereas this lower energy, if you initialize with the image, over time it will just converge to actually the average gray value of this image. What we have here is we have a quadratic cost, quadratic data term, quadratic smoothness term. And we see we get a blurring, and often this is not desired in practice. Often you want to remove noise, you maybe want to remove small scale structures, but you want to preserve the signal, or you want to preserve, say, sharp discontinuities. It turns out you can do that, and one way to do it is to modify the cost function. And to show you a little bit the power of variational methods, of what you can do with variational methods, we have the cost function, we have an algorithm to solve it, and now all we need to do is tweak the cost function in a way that better suits our needs. Let's say we want to penalize smoothness, so we penalize the gradient, but not too much. We don't want to penalize the gradient quadratically. Quadratically means that if the intensity change is twice as much, it costs 4 times the penalty. So a jump from black to white costs a whole lot, and this is why it's getting blurred. Let's say we drop the square here and just penalize the gradient, but without the square. So different cost function, just a tiny change, and this is the result you get. So here we have the cost function with the square, here the same cost function except we drop the square. And you see that if we blur that, or so if we minimize this energy, say by a gradient descent, we also get the smoothing, fine scale structures disappear, but some semantically relevant structures are preserved. For example, the hat here, the outline of the hat is exactly the same as in the input. It's not affected. And so all of a sudden, just by changing a tiny little bit in the cost function, you get a completely different behavior. You get a completely different process. And what's nice is for variational and optimization methods that you don't have to work on the level of the algorithm and go into this, sequence of processing and tweak there. You can do the tweaking on the level of the cost function. Change a little bit in the cost function and see what behavior comes out. Because all the rest after the cost function is more or less a standard processing pipeline that is essentially automatic. So you can do modeling on a fairly high level. You don't have to worry about algorithmic details. You don't have to worry about how do I determine, what structures to preserve, what structures to blur. Here you just change the cost function and the rest comes out automatically. Automatically means you take the cost function, compute the Euler Lagrange equations, the gradient descent. All of this is kind of a standard technique because derivative computations are straightforward. Here is a visualization of this process, and this was one of the breakthroughs of variational methods and partial differential equations. In the early 90s, people came up with these kinds of algorithms. The first one is actually an algorithm that is frequently cited by Perona and Malik, 1990. 2 researchers on the West Coast. Pietro Perona is at Caltech, Jitendra Malik is in Berkeley. They're both quite active today still. And in 1990, they proposed the so-called Perona-Malik approach. And it's essentially what you have here. It's an approach that preserves, that smooths, denoises images, but preserves semantic details. And I find this is actually much more fascinating to look at than this general blurring. And as we saw, the only difference is, in some sense, we drop the square and get something that is penalizes the gradient, but not quadratically. I should say Perona and Malik were not working on a variational level. They were working on the partial differential equation. But you can do these things on the variational level. That is actually something that was proposed in 1992. Rudin, Osher, and Fatimi. 1992, they proposed this exact cost function for denoising of images. And I should say this is one of the most powerful denoising techniques to date. It's extremely simple, as you can see, but it actually works quite well. The reason why this one is very popular, I mean, another thing you could do, of course, is you could say, oh, if let's say I want to penalize the gradient, but not so much. And here already I get improvements. Structures are preserved by dropping the square. So why don't I go even further and say nabla u to the power of p dx, and then I take p less than 1. So we had p equals 2. This is p equals 1. We can take p equal less than 1. Say, for example, p equals 0.5. That means we take the square root of the gradient. We still penalize the gradient, but we don't penalize as much stronger gradient. You can do that, and it's been done, and it works, but the difficulty here, and the reason why this is still among the most popular and powerful ones, is this is convex. Once you go to the square root or something smaller than 1, you lose convexity. Because the square root obviously looks like that. It's a non-convex function. Whereas if we penalize with 1, this is convex, and quadratic, this is p equals 2, p equals 1, p less than 1. And you can see p equals 1 is still convex, whereas once I go below 1, I lose convexity. And once I lose convexity, I have no guarantee that I am computing the optimal solution. So there's a trade-off in optimization, as always, and we see it very explicitly here, that the trade-off is between what you would like to minimize and what you can minimize. This we can minimize, this we can minimize. Once we go below 1 with the exponent here, we no longer have provably optimal solutions. And so there's the trade-off there. Of course, we can take p less than 1, say 1/2, and do gradient descent. As I said, you can always apply gradient descent. But if you have a non-convex energy, you get a solution. It may well look very good, but you don't have a provably optimal solution anymore. Yes, both of these works actually are very heavily cited. Not surprisingly, because these are some of the pioneering approaches to do adaptive denoising, to denoise but preserve structures. And so these are cited thousands of times. Here we see it again, so this is this kind of Perona-Malik type diffusion. Or this is called Perona-Malik. I should mention this is called total variation, because the gradient norm of the function written here is called the total variation of u. And total variation algorithms are extremely popular today. A lot of what we do in research is actually based on the total variation. To summarize, or not summarize, but to give you a little bit of a historic glimpse, I sometimes find that illuminating to see who are actually the forefathers in this domain. And the variational methods have a very long tradition. They were actually derived as much in research in physics, where people considered extremality principles. For example, they would say, to give you a very simple example from physics, let's say you have a wall here and you have a wall there, and you fix a rope at two ends of the wall, and then the rope typically hangs through in this way. But the question is, can you compute, if I tell you the rope is fixed here and here, if I give you the length of the rope, can you tell how exactly the shape of that curve is? And that's possible, and the way you do it is by variational methods. Namely, you set up an energy or a cost and say the rope is going to go into the configuration of lowest cost. And then you can compute that. And these and other problems were what initiated the variational methods. Because what you're computing, the specific shape of the rope, and from experience, is not going to look like that. But, who knows exactly, right? This curve is a continuous curve, so there's a function that represents the solution, and then I can associate with each possible solution a cost or an energy, compute the minimum. And these techniques, the mathematics behind it, were devised by Euler and Lagrange, among others, one should say. And Euler, you've most likely heard of Euler. If you had not heard of Euler, that would be very bad. Euler is probably the most influential mathematician, or definitely one of the most influential mathematicians in history. He got very old, at least for that time, surprisingly old. And he was very prolific, so he published tons of papers. Nowadays, as researchers, we are basically paid by the numbers, and we are paid by the numbers of papers we publish. At the time, that was not the case, and so it's actually quite surprising that he wrote almost 1,000 publications and books. Another surprising thing about Euler is that he was most prolific in the last 20 years of his fairly long life. That is very unusual. Typically, mathematically, talent shows up in the beginning of life, and once people are 35 and 40, productivity goes down. At least if you look at the numbers over the history, you see that. And it's quite unusual that someone is so prolific in the last 20 years of his life. As I said, he's generally considered the most influential mathematician of the 18th century and maybe beyond. My guess is maybe he had a lot of the papers in the drawer already, and then towards the end of the life he decided to submit them. I don't know exactly. He had a lot of children and grandchildren, and one of the things that is told about him is that he was very concentrated, so he could work on proofs and mathematics while his grandchildren were playing around his legs at his table, etc. And you may know a lot of the contributions he made. So the Euler number, for example, the little e that you all know, the Euler angle, Euler formula, Euler theorem. Typically, when someone says Euler formula, you have to check which one, because there's lots of Euler formulas. So, not surprising if you have 1,000 papers on a lot of important topics. There's lots of equations, the Euler theorem, Euler equations. For liquids, for example, there are so-called Euler equations that govern the motion of liquids, fluids, and the Euler Lagrange equations here. This is Euler. This is Lagrange. The name is misleading. Joseph Louis Lagrange is actually not French, although the name indicates that. He was born Giuseppe Lodovico Lagrange. He was Italian. But he had French ancestry in the family, and he was so proud of his French ancestry that at some point he changed his name. That was so to basically reflect that French ancestry. And he was an autodidact in the sense that he taught himself. And he got the chair for mathematics in Turin at the age of 19. That nowadays looks weird. How can you become an important professor at 19 years old when in Germany you just leave high school? It is impressive, but you should keep in mind that the times were different. The amount of knowledge that you had to learn was smaller. And so it's often hard to compare these times to modern times, where you go through high school 12 or 13 years, where you do university another 6 years, and then the doctoral degree, etc., etc., etc. So you cannot really compare. The requirements that are necessary to become a professor in mathematics were not the same. Maybe also the regulations were not as strict as today. He worked in Berlin for a substantial period of 20 years and then later moved to Paris towards the end of his life, and he wrote several books. Here again you see the reflection of his French ancestry. His books are in French, Mécanique analytique and Leçons sur le calcul des fonctions. So, and this is the lectures on functional calculus, and so this is where a lot of these ideas are developed. Yes, so that I wanted to give as a summary on a short intro on variational methods and the pioneers behind it, Lagrange and Euler, who coined the name Euler Lagrange equation. And in the next class we will then go into how to apply these techniques, the variational techniques, for dense 3D reconstruction. Thank you.